Hello, my name is Kyle Lindsay, and I'm the President/Chief Engineer for Xipiter UAS team here at Mississippi State University. Our team was founded in 2004, and this year will be our 17th year competing in the SUAS competition. Our team is broken down into 4 main sub-teams. We have an airframe team, an avionics team, a CAD and simulations team, and a software team. Each of these sub-teams has their own team lead. For airframe, it is AP Anshuman Behera. For avionics, it is Chase Kincaid. CAD simulations is run by both Sterling McGee and Turner Down, and software is run by Grayson Winham. So now we're going to go on to the requirements and acceptance criteria for our aircraft. So how did we develop our requirements? Well, the first thing we did was we read through the rules for this year's competition. After reading through these rules, we compiled a list of all the requirements that our aircraft will have for this competition and its mission. Then we read through the FAA, FARs, to see what regulations there are required of our aircraft. And we also went through some of the AMA safety guidelines to see what is some of the best practices for UAS construction. After compiling a big list of all of our requirements, we created some system model diagrams to help us figure out what was required of our aircraft. So one of these diagrams that we created is called a functional flow block diagram, or FFBD. It's basically a block list that shows all the different aspects of a mission and what is required of the aircraft during those parts of each mission. We also created a flight profile for our aircraft. Basically, this just gives us an outline for all the different stages of our flight. We also have our altitudes and range for each portion of each flight. After compiling our list of requirements, we started to do some background research. So we looked at papers from previous years, we looked at some of our aircraft that we designed previously, and we also looked on the internet to find other similar aircraft to try and get a good idea of things that have worked and things that have not worked in the past. So after compiling all of our research, we figured out that we'll approximately need an aircraft that's around 35 pounds to be able to cover a 12-mile course while hauling 5 water bottles for the payload delivery mission. So after we kind of did our background research and figured out what minimum requirements we need, we created what's called a matching plot. This uses a bunch of equations to create lines of minimum performance. So the plot itself on the y-axis shows the minimum power required for each different phase of flight, while also having the wing loading required at that given power requirement. So using all these different lines, we found an optimal point. For us, we found that an optimal point would be at a wing loading of 4.5 with a power requirement of 1.2 kilowatts. Next, we needed to start kind of looking into more specifics about our airplane, right? So the next thing we started to look into was propulsion. This year, we decided to go with electric. We originally were going to go with gas, but due to the maintenance requirements of some of those gasoline motors and some of their operational problems that can occur, and also noise and safety concerns with gasoline engines, we have decided to turn to electric. They're very simple to use and a little bit safer. So to reduce our total power consumption, instead of doing one large electric motor, we decided to do 2 smaller electric motors to make our aircraft more efficient. Additionally, we've decided to go with a V-tail design. This design simplifies the construction process because we're removing one of the tailplane surfaces that we need to create. So it'll help expedite our design process. This does have some drawbacks though. Because of the V-tail design, our tails did have to be larger, increasing the force on the tail. And it creates a little bit more complex of a wire mixing problem. However, Q Ground Control and RD Pilot Mission Planner have presets for V-tails, so most of these problems are able to be kind of minimized. So next, we had to kind of decide what materials are going to make the airplane on. How is the structure going to be made? So for this year, we've decided to go with primarily carbon fiber, where you're using an 8 hardness pre-impregnated carbon fiber resin system. This is a resin system that's just a carbon fiber sheet that already has the resin in it, making it extremely easy to work with and very repeatable. Where you're using this material because a lot of it was donated to the team from the Advanced Composites Institute at Mississippi State University. So our material is free, and this material also has an amazing strength to weight ratio. This material does have some drawbacks though. Because it has the resin already inside, it must be cooked in an oven to be able to be cured under pressure. Because of this requirement, making molds can be extremely expensive. So to minimize cost, our team decided to go with a primarily flat plate faceted design, kind of like the F-117, to help ease our production and minimize cost of production. And now Maggie will talk about the actual fabrication of our airframe.
So this is our airframe table, which is where we do the main bulk of our work on the airframe sub-team. So as Kyle mentioned, our airframe is assembled of mainly 90% carbon fiber. So the first thing I want to talk about is our fuselage. What we did was we did a few flat stock layups of pre-preg carbon fiber. And that process consisted of us laying down a piece of carbon fiber on a flat steel plate, and then layering over it is a peel ply, perforated plastic, breather, and wrapping it in bagging. Now we put that under suction for overnight, and then we cured it in our oven for about 6 hours. We cut those pieces so that they could fit together almost like jigsaw puzzles. And we glued those pieces together so that they would form a rectangular box structure. Now for our wings, the first thing we fabricated was our main wing spars. Now those were fabricated with 8 plies of pre-preg carbon fiber, as shown here. So in the middle we have 4 layers of carbon fiber at a 45-degree orientation, sandwiched by 4 layers of carbon fiber at a 90-degree orientation. We performed the same layup process I discussed earlier, put it under bagging, cured it in the oven. So next we used this flat stock here and cut out our ribs, as shown here, using the water jet. So the next part of our process involved cutting foam core into the shape of our airfoil. Now I will note that this is low density foam core, and what we used on our actual aircraft was high density foam. So these were cut into the correct airfoil shape, and then the wings were assembled, as I will demonstrate in just a second. So now I'm going to talk about the fabrication of our aircraft and how it all came together. So starting with the wings, we mounted the ribs to the main spar and put each piece of foam core in between the ribs and glued them in place. We also did a fiberglass layup over each wing to add some structural integrity to our wings. These wings were installed into the fuselage by mounting a spar block on the inner part of the fuselage and sliding them in each way, and they will then be bolted to that spar mounting block to hold it in place. So the tail components were fabricated in a similar way to the wings, with the foam core in the shape of each airfoil that was chosen, and with hinges to mount the control surfaces. A 3D part was printed for the tail boom to ensure that the tail feathers were in the correct orientation. As for the main gear, that was bolted to the bottom of the fuselage for both, and the nose gear was bolted to the front as shown here. The engine mounts were installed by creating some 3D printed parts and drilling holes in our main spar and attaching those mounts to the main spar as shown here. And lastly, we will have a nose cone and engine nacelles. These will be made of molded plastic. Now I will note that all of our fasteners meet the rules and requirements for the locking mechanism. All of our fasteners use Loctite or lock nuts.
And now Sterling McGee will explain the payload mechanism and the camera gimbal we used on our airframe.
One of the main things that we designed for this competition was the bomb bay drop system. It is a spring-loaded system, mainly designed to be 3D printed. The basics of it is 2 concentric rings will be held around the water bottle, and those rings will be held into a spring-loaded locking mechanism. And a servo mounted in the mechanism will be actuated to compress the spring, which then would allow the water bottle to fall out of the plane. So for the camera mount system, it was designed to be placed on the front of the plane here. using SolidWorks and mainly made to be 3D printed out. It uses 2 servos to be able to actuate the camera up and down and to rotate it side to side, which would give us a full motion that we need for our camera system.
And now Grayson Winham will explain our software and wiring for this year's aircraft.
For object detection, once we obtain an image, we'll conduct a frequency analysis to find out the color abundance in the image. And then once we identify the most abundant image, which will very likely be the color of the runway, we'll determine an approximation for this color and then replace every other color in the image that doesn't meet this approximation with a different color. And then we'll conduct a binary threshold to isolate those colors, and now we can do a contour detection on our new image, which will give us the bounding box of every potential marker. We will then rotate these bounding boxes so that they're upright. Then each cropped image will be up or down scaled to meet requirements for the machine learning model, which we'll use for classification. The machine learning model will be used to classify the shape and the alphanumeric in each potential marker image. And then we'll use a color frequency analysis again to identify the color of the shape and the alphanumeric, with the most abundant color likely being the shape's color, and then the second most abundant would likely be the color of the alphanumeric. For localization of these markers, given the UAV's telemetry and then the position of the marker in the original image, we can then get a rough approximation for the GPS coordinates of each marker. The autopilot of the UAV will be using the ArduPilot flight stack to manage the majority of the overhead of the actual flying of the aircraft. And then we will use ROS to coordinate the individual actions. The autonomous flight for the mission is as follows. The UAV will perform a manual takeoff and then fly the waypoint course. Once it has completed the waypoint course, it will navigate towards the payload drop zone and then perform a survey path over the drop zone, which will consist of bisecting the payload zone multiple times in correspondence with the FOV of the camera. And while it is doing this, it will be taking images of the ground for object detection, classification, and localization. Once a marker or markers are found, they will be compared with the currently loaded payload in the UAV, and if a match is found, a waypoint course will be generated to intersect the marker. Then, using parachuted kinematics, the distance before the intersection will be calculated and the payload will be released. This process will be repeated until all the payloads in the UAV are dropped or none match the currently identified markers, and then the UAV will return to land to either have new payloads loaded into it or to terminate the mission as all payload drops have been conducted. For all this to be communicated with the ground station, our aircraft utilizes a set of ubiquity radios that operate on a 5 GHz frequency band with a data transfer rate between 100 and 500 megabits per second. We also use a 900 MHz Dragon Link radio transmitter for the manual control of the aircraft. For the detection and avoidance of other aircraft in the airspace, we are planning to use the camera feed and similar image processing techniques used to identify markers to identify other aircraft and avoid them.
So what were some alternatives that we thought about while we were designing our aircraft? So some of the major alternatives we thought about was electric versus gas, right? As discussed earlier, gasoline engines can be kind of tricky to set up. They have a lot of maintenance requirements and they also create a lot of mess and noise. Additionally, there's rules this year added to the competition to where students aren't allowed to get within a safe distance of a prop arc, and if you're handling a gasoline engine, you have to stick your hand on a propeller blade to actually start the motor, and the tuning for the carburetor is very close to the propeller arc. So to avoid having any interference with the rules, we've decided to go with all electric. Additionally, electric is a lot easier. You just kind of plug it in and hit go. Gasoline engines require starter motors, batteries, alternators, and a lot of other systems to make them work correctly. So overall, electricity is a quite simple way to go. The only downside to doing electricity is weight. Batteries have a diminishing return on endurance. So trying to find the right balance between number of motors and battery size took us a little while to decide upon. One of the other main topics that we were discussing was tail orientation. A traditional tail is very simple aerodynamically to analyze. However, it's got more components, right? All these different components add time and cost to the actual build of the aircraft. So in order to kind of eliminate some of that extra complexity time-wise, because we knew we'd be cutting it close on production schedule, we decided to opt for a V-tail design. And we'll use the presets in Q Ground Control and RD Pilot Mission Plan to help alleviate some of the control mixing issues that are common in V-tails. Another kind of thing that we were looking at was different types of bomb bay door drops. So right now we've got just a simple open hatch that has a pin that drops the water bottles. Some of the alternative methods that we were looking at was a rotary bomb bay door. So basically our water bottles would be loaded in a drum and then rotated out of the fuselage. This would be simpler, however it is very heavy and is very large. So we decided to go with our more size optimized method versus the simpler method. So now we're going to discuss about the safety of our airframe. So some of our main safety concerns were structurally. Is our airplane going to be strong enough to handle all the loads in flight, right? So after we designed a lot of our aircraft, instead of just doing analysis on our structure, we also did testing on our structures. We did spar loading testing and drop tests of our fuselage to ensure that our aircraft would be strong enough to withhold all of the loads it could possibly see in flight. Some of the other things we're worried about safety-wise is, assembling the aircraft. So during assembly, we have more than one person checking everything that goes together, and we have a person designated as our quality control person. So after anything gets done, that quality control person must double check whatever gets built. Additionally, when we actually go and assemble the aircraft to go fly, there's a lot of hardware that has to be put together and double checked. So we've created checklists that the pilots will go through and double check every single nut and bolt on the airplane to ensure that everything is safe before flight. Furthermore, we've created guidelines for how we're going to operate. Every single time we go out and fly, we create a flight test document. This document outlines everything that the mission is going to cover. It also covers any safety things that might need to happen, like don't walk too close to the propellers, keep the airplane on ground at all times unless you're ready for takeoff, that kind of stuff. So we've developed a lot of procedures and checklists and documents to kind of help brief everybody who will be at the flights about all of the different safety hazards and stuff before we start flying. Additionally, we have color-coded shirts and high-visibility vests that will be used during flight to ensure that all the flight line members are very visible during the flight. As far as flight readiness goes, we have sadly not yet been able to fly. We are planning to fly later this week though. However, we have completed all of our structural testing, so we know that our aircraft is structurally sound enough to perform flight. We will perform our flight tests this coming weekend, weather permitting. In conclusion, we have designed a brand new aircraft named the Xantis. This aircraft will be primarily made out of carbon fiber, around 95%, allowing it to have a very good strength to weight ratio. Additionally, we have gone with an all-electric design to make sure that it is very quiet and reliable. Furthermore, our aircraft will be a fixed-wing aircraft utilizing a V-tail design, and will have an endurance of about 40 minutes or a range of about 24 miles. So we should be able to run the competition twice. We would like to thank our sponsors, Faculty College of Engineering, ACI, Scorpion, and High Tech Service for their generous donations of both material and money this year to allow us to operate. Thank you.